So let's begin. What I'm going to talk about is a small introduction to ray tracing, acceleration structures, and traversal. And I will try to give you an overview of existing CPU and GPU ray tracing libraries that you can just plug in and use. I will talk a bit about how to design GPU ray tracers. And I will try to show you a couple of examples that either we've done or are present in the SDKs for some of the ray tracing libraries that I'm going to cover. And finally, I'm going to show you our motivation for using ray tracers in the Holografika displays. Okay, so what is this ray tracing all about? We want to render images by evaluating interaction of light beams of an emitter with surfaces of various materials. Basically, we are shooting rays of light from light sources, and we check their path through space. Whenever they hit something, we evaluate what happens with the light beam. We have the ray definition in a parametric form, and we need the following functionality. We need ray generation. So we have an emitter, and we need to know the shape of it to be able to generate rays from its surface. Or the other way around, we can generate rays for a camera. If we have a camera model with some kind of lens, then we can generate rays for the pixel XY of the camera. We need to have something that tells us if there are any hits on the ray. We need to know if the ray is missing all the geometry, and we need to know which is the closest hit of the ray to its current position. When we do the hit point evaluation, then we need to know when the ray is hitting the surface, what is the hit point. And if we are hitting some kind of acceleration structure or some solid surface, we need to know the incoming and the outgoing hit point as well. And we need something for shading, so we need to know some kind of material properties so we can evaluate the color. So why is this business important? We have rasterization, right? So it works, it's fast. Why ray tracing? We have a couple of disadvantages for the rasterization, which is basically linear interpolation. When we rasterize a triangle, it's linearly interpolated. And this is fine for basic pinhole camera models or orthographic camera models, but it's not really nice for anything with a lens. Because if we have some kind of spherical coordinates, then we are not able to interpolate the triangle correctly anymore. We cannot change the projection per fragment. This is basically the same thing. So we cannot reproject a fragment when its position, its pixel position is already decided, then there is nothing to do. So basically we want to use rasterizer wherever linear interpolation is working for us, and we want to use ray tracer everywhere else. Ray tracing is costly due to the traversal of the ray in the triangle soup, so we need to use it sparingly. We need to be sure that we need to trace additional rays and that it will improve our image. Okay, just some basic geometry. If we want to have a camera, then we can emulate the near clip plane with a plane, so we need some kind of ray plane intersection code. If we have a point, so like if we have 2 points on a plane and a normal n, then we can define we can have the definition of the ray, and then we can solve for t to get the intersection point. We also need a ray triangle intersection. Most of our geometry is triangle soups, so we need to determine the t parameter again. So if we are hitting the triangle, then we need to determine the hit point on the triangle. Okay. If we want to accelerate, we have two choices. Either we can use bounding spheres or we can use bounding boxes. if we use bonding spheres, they usually don't cover our geometry too much. There is too many empty space in a bonding sphere, but still there are some use cases where spheres are more optimal than bonding boxes. So I will just very quickly show you how to do ray-sphere intersections. So again, as I've told you in the beginning, when we talk about acceleration structure, we need both the incoming heat point and the outgoing heat point, so that if we miss the triangles inside the acceleration structure, we can continue towards the next bounding sphere or the next bounding box. And of course, we will need ray intersection with an axis-aligned bounding box. This is a small code for that. Again, these are very quick tests, so this is why we are using these acceleration structures, the sphere and the box, so they can be very easily determined. Building a sphere is linear, and building the bounding box is also linear, so they can be done very quickly. Okay, we can talk about two versions of ray tracing. We can talk about forward ray tracing when we start rays from the light source and we follow the ray's traversal path. And if the ray happens to hit the camera, then everyone is happy and we choke up some color in the pixel of the camera. Of course, if the camera is not a pinhole camera, but comes with a lens or some kind of more serious geometry, then even hitting the camera lens can be a challenge to evaluate. Backward ray tracing starts from the camera. It generates a primary ray, and then it follows the path of the primary ray backwards and checks whether there is any contribution from lights. Usually, we start additional rays to evaluate reflection, refraction, and shadow. Okay, so I've already told you that we can build some kind of acceleration structure to speed up checking whether the ray hits anything. We can do this in two ways. We can have an object partitioning scheme where we surround our geometry with some kind of bounding box or bounding sphere. And we can have a spatial partitioning scheme where we have a section of space that we want to partition in multiple subspaces. And basically, there are two versions of this spatial partitioning. One of them is the oak tree, and the other one is the KD tree. The oak tree always divides space into 8 additional subspaces along the XY, XZ, and YZ planes. And the KD tree is usually using a single axis per split, and it cycles through all the axes. So basically, XYZ, XYZ, XYZ as we go down deeper into the acceleration structure. We have to select a median where to split, and we need to split into the left child and the right child based on the median. This is an important heuristic that we can use to find the median, which is called surface area heuristic. We calculate the surface area for all triangles, and then we split so that we have an equal surface area, or like as close to equal as possible surface area for both children. Okay. So there are a couple of improvements that are GPU friendly to these acceleration structures. One of them is the SBVH. It's a split bounding volume hierarchy. And the nice idea about this is that it mixes the object and space partitioning schemes, and it tries to select the optimal one. So first it tries to find an object split, then it tries to find a spatial split, and it tries to select the winner based on this heuristic that I've shown you, the surface area heuristic. It uses binning, so it pre-partitions the space before it tries to find the split. And it holds the complete axis-aligned bounding boxes, as opposed to the KD trees where we only store the splitting plane. It's also very important that it can reference the same triangle in multiple bounding boxes. This is something that you generally want to avoid in BVHs, but as it mixes the spatial partitioning there, it can happen that the splitting plane is splitting a triangle in half, so you have to put one part of the triangle to one. So like you have to put the triangle in both children, basically. Okay, there are two things about acceleration structure. One is the traversal cost, like how fast can I traverse. The other one is the build cost, how fast can I build my acceleration structure. If I have static scenes, I don't really care about the build cost because it only happens once. But if I have a dynamic scene, then I need to employ some kind of acceleration structure where the build itself is fast enough. And one such acceleration structure is the TR-BVH. It constructs a low-quality BVH as a first step. Then it splits triangles with another heuristic, not the surface area heuristic, doesn't matter, before the BVH construction. So even before it starts building the acceleration structure, it tries to check whether we have a triangle with a large area. And if we have a triangle with a large area, then we try to split it so that when we actually build a BVH, we only have the triangle which is small enough to be in a single bin in our acceleration structure. It stores all the nodes in a 60-bit Morton code, which is an interleaving code. It defines a z-order curve in space, so it's a 3D z-order curve. This improves locality quite well because nodes that are close to each other have very close Morton codes. Like nodes that or bins that are very close to each other in space have Norton codes that are not far away from each other. So it improves the locality. Okay, so once it has done the pre-split, it starts to build a BVH, a tree structure in the local neighborhood of nodes in the smaller bins, and then it uses dynamic programming to improve these treelets, these small subsections of the BVH, and it's searching for the optimal topology at the local neighborhoods, and it goes from bottom up, so it generates acceleration like ABBs for the triangles first, and then it tries to optimize the subtrees so that we have a balance on the tree that is good enough for the acceleration structure to provide quick traversal. Okay, so what do we need to use when we are below 7 million rays per frame? Then it's best to use BVH because it builds fast and there are no duplicate triangles on the acceleration structure, and this behaves the best. When we have between 7 million and 60G rays per frame, you can use TR BVH, and above 60G, it's worse to use SBVH, even though the build times are much slower for the SBVH. Okay, what kind of acceleration libraries are available? Of course, we have CPU accelerators, many CPU accelerators for ray tracing. Maybe the best one is Intel Embree, which is a CPU ray tracer. It has support for all kinds of meshes, triangle and quad meshes, subdivision surfaces, cubic spline curves, and user-defined geometries. It supports motion blur, so that's why it has a different acceleration structure. The STBVH, which is a spatial temporal BVH, so it also takes into account the animation, like how the mesh would actually move from one frame to the next when it generates the acceleration structure. Okay, let's talk about GPU acceleration libraries as well. We have NVIDIA Optix, where we have a context. And when we launch the when we set up the context and launch the context, it goes into ray generation, so it generates the primary rays. So we can already see that this is more or less a backwards ray tracer, or at least it likes to behave that way. Then we have Raytracing, where we do node graph traversal. We have a traversal on the nodes. We have a select visit program that can determine the level of detail of the mesh that we want to investigate. We have acceleration traversal, and we have the intersection, which goes into the AnyHit program. And if we hit anything, then we can get to the closest hit program, and here we evaluate the shading. So either in the AnyHit, the closest hit, or the miss. So the miss usually evaluates the cube map or the environment map. AnyHit usually evaluates shadows, and the closest hit evaluates the materials. Okay, so what are the features that are present in Optix? First of all, it's based on CUDA, so it plays nice with other CUDA codes. It supports bounding box generation. There are no bounding spheres. Supports custom intersection, and currently there is no default intersection available for meshes. I'm pretty sure that this is going to change because NVIDIA have now hardware support for intersection of meshes in their novel hardware, in the voltage generation GPUs. So I'm pretty sure that there is going to be a default intersection very soon in NVIDIA Optix as well, because they are going to build it again on top of the RTX driver. It supports instancing, which is very nice because instances have the same bounding boxes. They just have different transforms. So it supports TRBVH, SVVH, and BVH as acceleration structures. It supports basically everything that CUDA supports. So bintless buffers are available, bintless textures are available, cube, layered, map textures are available. There is built-in support for motion blur. And it's very important to know that traverse and shade are done in the same call, so the stack depth is limited. Everything is done in a single call. Traverse calls shade, shade calls traverse, and so on and so forth. So you cannot have many bounces when you evaluate your shading. That it's simply the stack depth is limited. This also implies that shared memory is partially used by emulating a stack. It's also worth to note that we have a built-in AI accelerated denoiser, which uses tensor cores to denoise the results of the ray tracing. Okay, let's talk a bit about scene management. So we have basically a group on top. We have transforms. So transforms are not used for static scenes; they are only for dynamics. We can decide for acceleration in the group, in the geometry group, and we have instances here which cover some kind of geometry. Okay, so we can instance the same geometry with more geometry instances. The selector can choose between level of detail meshes, which can have different acceleration. Okay, from AMD we have the Radeon-Rays SDK, which provides intersection and occlusion query only. So this is only the traversal part. It supports backends, OpenCL, Vulkan, and Embree. So this is both CPU and GPU. It works on basically anything, but it was designed for AMD architectures, and it shows. I will talk a little bit about that later. Okay, so it supports BVH, quad BVH, and hierarchical linear BVH, which has very fast builds, and it works very nicely on the GPU. It supports surface area, heuristics, and median for splits. They've also built a renderer on top of the traversal, which is called Baikal. And it is a high-level ray tracer renderer. So it supports materials, textures. Unfortunately, there are no texture rays, lights, volumes, and so on and so forth. Monte Carlo ray tracing, motion blur, post-processing. And the nice thing about this is that you don't need the stack. So traverse and shade are done in separate cores. You don't need the stack, so you can use the shared memory for your own purposes. I will very quickly show an example of this. So as you can see, this is a Monte Carlo tracer, so it's noisy as hell. There is a denoiser that's trying to get rid of the noise, and it gets incrementally better if I leave the camera alone. You can see these nice, so there is an area light, so there are nice soft shadows. Also, it's a Monte Carlo tracer, so I don't see any diffuse interreflection, but there are some nice reflections probably somewhere. Okay. Okay, so this was the Baikal renderer. There is a new API called the Microsoft DirectX Raytracing API, where the building and traversing of the acceleration structure is left to the driver. This is very important. So future hardware acceleration can be built in seamlessly. Triangle geometry is handled automatically. This is also very important, so you are not able to do your own ray triangle intersection and ABB generation for your mesh. The attributes are very centric here, but it also allows for custom procedural geometry, but this will need intersection shaders. Everything is allowed that is allowed in DirectX compute shaders. You have a couple of additional functions on top of this for ray generation, traversal, accept abort, etc. And it writes results into UAV. Traverse and shade are again done in the same call, so the stack depth is limited. Again, you have no access probably to as much shared memory as you would expect. There is hardware acceleration on Volta, and there is fallback layer for other hardware. Profiling is available via PIX. For Optix profiling is also available via the CUDA profiler. Okay, so again, we have the trace ray. We check for candidate primitives. If we have found one, then if it's a triangle, then we go to the fixed function. If it's not a triangle, intersection shader. If we have intersection, then we either evaluate the any hit shader or the closest hit shader. And if we have no hits, then we go into the miss shader. You can also check out there is a top-level acceleration structure. This is the only place where you can do transforms, and there is a bottom-level acceleration structure that only handles geometry, either triangles or something custom. You can have access to shaders via a shader table, and then you can evaluate shading. Okay, I will very quickly try to show the D3D ray tracer example. This is now running on fallback layer, so I don't have any Volta hardware. Not many people do. Okay, just a sec. So yes, so this is the Sponza Atrium, and most of this is rendered with tracers. Okay, anyway, so you can see the ray trace shadows. I don't know if I can find anything that's shiny. Probably not so much, because this is like mostly stone. Okay, anyway. Okay, very quickly a few words about designing the GPU ray tracers. We have different functions that test the GPU very differently. Ray generation load depends on the camera model. Usually this is the easiest part if you have a simple pinhole camera. BVH traversal is very heavy on memory and scalar, so you need lots and lots of main GPU memory data. Shading is heavy on arithmetic and transcendal and vector operations. So ideally, we should split the workloads to separate traversal and shading. This is only done by the Radeon-Rays. If you want to go from rasterizer engine to tracer engine, what's the current workflow? You have to transform feedback your geometry to a common buffer. You have to separate static and dynamic. Pack materials, lights to SSBOs or some kind of unordered access view on D3D. Use binded structures for materials, light masks, and so on and so forth. Then use interrupt to transfer your data if it's necessary to either CUDA or OpenCL. Use the GPU tracer library, then use interrupt to transfer back to the rasterizer. Upload the texture from the buffer with a pixel unpack buffer, and then you can use this in subsequent raw calls or compute launches. Okay, how do we render for linear cameras? We render a G-buffer, then we have all kinds of data for our scene, and then we can ray trace on it at half resolution plus add a spatial temporal filter. I would like to show you very quickly an ambient occlusion example. Okay, so the left one is an SSAO, and the right one is ray traced, unfiltered. And this is the difference between ambient occlusion. So we are calculating the occlusion of the geometry on itself. So we can have some kind of evaluation for ambient lights. Of course, this should be filtered before applying it to the model. This is running on Optix right now. So rasterizer once, G-buffer evaluation. This is the original SSAO, and rasterizer, so like G-buffer evaluation a second time with the ray-traced ambient. Yes. Okay, for shadows, we trace shadows, shadow rays to lights. If there are any area lights, then we need multiple rays for soft shadows also, and we need to filter the traced shadow rays. For reflections, we need at least one reflection ray, plus we can use additional rays where the luminance is high. We can check this on the G-buffer. What do we do with ray tracing at Holografika? Our camera model differs very, very significantly from the pinhole camera. So we've implemented the primary ray generation for holographic light fields with additional multi-sampling, and we have built a Whitted ray tracer for static scenes on it. We've built it on OpenGL, so we don't need to care for the interrupt. We generate the primary rays. We generate the BVH3 on C++ code, so on CPU. It's a binned surface area heuristic method construction. Then we do traversal and shade in two passes. First, we do a stackless traversal, and we collect all the intersection data. We use the materials to check whether we need additional data, and then we evaluate the color in another shader. Okay, I will show this also very, very quickly. Yes, so there are very few lights for this one, but and it's for 2D, so we've also implemented it for 2D. But you can believe me that this also runs on Holografika displays with the enhanced camera model. Okay. Okay, that's it from me. Thank you very much.
No, then I will ask this choice between the vendors, whether it is separated paths for AMD for the traversal and the shading and the stack limited case for the others. For me, I'm not an expert, it sounds like a deal breaker for the CGA films, they need lots of bounces, and they would push the stack to the limits. So it would mean that AMD would be much more suitable for the high-end filming industry.
Yeah, I would say that for high-end, simply the GPU memory is not big enough. Basically, not even because of meshes, but because of materials. So the materials are quite big because they are not using like simple material models. So I would say that they will stick to CPUs as long as the GPU memory is not increasing to like tenfold or something. But yes, for sure, the AMD model fits them much better, I think.
Find the Holografika stand back, and we'll thank Attila again for the talk.
Thank you very much.